So this video is going to go over the product property of square roots, or more in general, the product property of radicals. And what it says is what I have written here. If two or more numbers are being multiplied under one square root sign. So for instance, maybe I have the number 16 times the number 25, and they're both being multiplied together under one square root sign. What it says is we can rewrite it by giving each number its own square root sign and connecting them with the original multiplication. So I could take this and rewrite it as the square root of 16 times the square root of 25, which is easy, right? That's just 4 times 5, which is equal to 20. Now it works for more than just one number. So if I put it in general terms, if I have a bunch of numbers like A, B, and C all being multiplied under one square root sign, every number that's being multiplied gets its own square root sign, and we connect the individual square roots with a multiplication symbol. I do have two other ways that you can rewrite the same sentence, but this is our product property of square roots. It's a way to rewrite a square root as separate square roots. Now we use these properties, specifically the product property of square roots, to simplify expressions that have square roots in them. So I've defined what we mean to simplify it. When I have a square root, I'll know it's simplified if there's no perfect squares under the radical sign. So like if this was the square root of 50, I should evaluate that. Another thing that it means to be simplified is there's no fractions under the square root sign. And then another definition of simplifying that we'll pay attention to at later videos more specifically is we're not allowed to have radicals in the denominator of a fraction. So for instance, if I had a fraction like 1, I can't have a square root in the bottom. That's just not allowed. So the types of problems that we're going to do is like I have up here. So how would we simplify a square root? Well, the first step that we need to do for using the product rule is we want to rewrite the number under the square root as the product of two other numbers. Now, one of those numbers needs to be a perfect square. And I have a list of perfect squares if you're not familiar with them. But in other words, the perfect squares, which are in purple here, are numbers that we know the square root of. So I want to take the number 50, and instead of writing it as 50, I want to write it as the product of two other numbers. One of those numbers I need to know the square root of. So I'm looking at my list of perfect squares, and I see that I could use the number 25. Because I know the square root of 25 is just 5. So if I rewrote this as the square root of 25 times 2, I've changed the way the problem looks, but I haven't changed the value. So once I'm able to rewrite the number as a product, I can then split the square root into two square roots. So instead of just having the square root of 50, I could split it up into the square root of 25 and then the square root of 2. Now, the reason that I used 25 was because I know that this is a perfect square, so I know the square root of this number. So that's step number 3, is evaluating the known square root. So I know the square root of 25 is 5, and then I have the square root of 2. Now, we just want to verify that it doesn't simplify anymore. What I mean by that is check the number that's under the square root sign. So I look at the number 2. Would I be able to rewrite that just like I was starting over? Could I rewrite the number 2 using one of my perfect squares? And I cannot. So this signifies this is our final answer. So we go back and check our requirements for simplification. There are no perfect squares under the square root, nor could I rewrite the number 2 as the product of two numbers, which one of them was a perfect square. There are no fractions under my square root sign, and there's no square roots in denominators. So this is our final answer. Here's another example. We need to simplify the square root of 196. Now, the reason we include this example is we do them all the same way. The first thing we would need to do is we need to rewrite the number 196 as the product of two other numbers, but one of those numbers must be a perfect square. Now, if you're not sure, what I recommend doing is check the perfect squares in order. So we're never going to check 1 as a perfect square, but the first perfect square that it could be is the number 4. So I'm going to use my calculator to see if 196 is divisible by 4. So when I type in 196 divided by 4, I get the number 49. So that told me I could take the number 196 and rewrite it as 49 times 4. So instead of the square root of 196, I can write this as the square root of 49 times the square root of 4. Step number 2 is telling us to use the product property. If I have two numbers under one square root, I can take that and split it up into two square roots. The first number gets its own square root. The second number gets its own square root. Now in this case, I actually know both of these square roots. The square root of 49 is 7. The square root of 4 is 2. And there was a multiplication in between them. And then we get 14. And obviously, we verify that it doesn't simplify anymore because it's just the number 14. So in this example, we need to simplify the number 48. So the first step we need to do is rewrite the number as a product of two numbers, and one of those needs to be a perfect square. So let's say I checked 4 because that's the first perfect square. So 48 divided by 4 gives me 12. So I found a way that I can rewrite 48. I can write it as the square root of 4 times 12. Now if I have one square root with two numbers being multiplied, I can give each of them their own square root. And then I can evaluate the known square root. This is a 2, and that's the square root of 12. Now this is an important example because we need to verify that it doesn't simplify anymore. But this one does, so I'm just going to show some more work over here. If I looked at the number 12, which is under the square root, there is still a perfect square factor that's under there, meaning I would be able to rewrite the number 12, so I'm going to keep the 2, but instead of 12, I could write that as 4 times 3. So now I would just repeat that process. If two numbers are under one square root, each of them gets their own square root. I can evaluate the known square root. The square root of 4 is 2. And then the square root of 3 is just the square root of 3. And 2 times 2 is equal to 4. So now I think I found my final answer. I'm going to go back and double check and make sure that there's no way I could rewrite 3 using one of my perfect squares. So 4 root 3 is the final answer. Now, it's fine to simplify things in more than one step. Just like when I have a fraction, it's okay to simplify a fraction in more than one step, as long as we get down to the final answer at the end. However, one thing that I would point out to you, if you find the biggest perfect square, it makes it easier. So 4 is a perfect square that goes into 48, but there's actually a bigger one. I could check and I would see that 16 also goes in to 48. So instead of writing it as 4 times 12, another option that I could have done, which we'll see is much faster, I could have written this as the square root of 16 times the square root of 3. So I could give the 16 its own square root and the 3 its own square root, which brings me down to 4 root 3. So looking for the biggest perfect square will make less steps, and it might be easier for you. So let's do another example. We need to simplify the square root of 108. And I don't exactly know how to rewrite that, so I'm just going to go check my perfect squares. So first I'm going to check to see if 4 goes into 108. So on my calculator, I'm going to 108 and dividing it by 4. And that one actually does give me the answer of 27. But before I do that, I'm going to make sure that there's no bigger perfect squares that go into it. Because if I find the biggest perfect square, it usually makes the problem a little bit faster. So I'm going to try 9 just to see if that one works. And I go to my calculator, 108 divided by 9 gives me 12. So that's another way I could write it, right? I could use 4 times 27. I could do 9 times 12. But maybe there's another bigger one. So let's try 16. Does 108, is that divisible by 16? On my calculator, I'm checking that. That one doesn't work. I'm going to try the next one, which would be 25. That one doesn't work. And then I'm going to try 36, because that's the next perfect square. So if I do 108 divided by 36, my calculator tells me that is 3. Now, I'm going to use 36 and 3 because I know the square root of 36, and 3 is a simple number. So instead of 108, we're going to rewrite our radical as the square root of 36 times 3. So if I have two numbers under one square root sign, I can give them each their own square root. And then I can evaluate the square root I know and keep the one I don't. When I go back to check if I have the final answer, there is no way that I can rewrite the number 3 using one of my perfect squares. so I know I'm done. Now again, it's really important to note that it doesn't matter which one of these we start with. Let's say I started with 9 and 12. I'm still going to get the right answer, but it's going to take me more steps because I didn't use the biggest perfect square. In this situation, as I'm simplifying the square root of 9 and the square root of 12, the square root of 12 actually simplifies more. I could rewrite that as 4 times 3. And I can again give each of them their own square roots. So the square root of 4 is just 2. So we get the same answer no matter which factor pairs we use, as long as one of them has a perfect square. But what we're noticing is the biggest perfect square leads to the least amount of work. If I don't use the biggest perfect square, I might have to do more than one step. The very last thing I want us to see is it works both ways. If I have two numbers, each under their own square root being multiplied together, I can put them back under one square root, because sometimes that makes the square root even easier to do. So as the last part here, what we're going to write is it works both ways. That is, if two radicals are being multiplied together, we can join them under one radical and multiply the original numbers. So just in the general case there, if I saw a bunch of square roots, like the square root of A times the square root of B times the square root of C, if I wanted to, I could put them all back under one square root. Like we see here, I don't know what the square root of 3 is. I don't know what the square root of 12 is. But when I plug them back into the same one, it's actually just the square root of 36, which I do know. So sometimes it's beneficial to go both ways. And that is the product property of square roots.